everyone. Welcome back to the second lecture of MLSS 2021. It is our great honor to have Professor Hsuan-Tien Lin as our speaker. Professor Lin is the professor of National Taiwan University. Between 2016 and 2019, he worked as the chief data scientist of AINTU-人, one of the most representative AI company in Taiwan. Professor Lin has many great achievements. He co-led the team that won the champion of KDD Cup in 2010, 2011, 2012, and 2013. Professor Lin is also well known in teaching machine learning. He received the Distinguished Teaching Award from National Taiwan University twice in 2011 and this year. This is very unusual because only the top 1 professor can obtain this award. He co-authored the very popular introductory machine learning textbook, Learning from Data, and co-authored 2 very popular machine learning online courses, Machine Learning Foundation and Machine Learning Technique. I believe almost all students who speak Mandarin have read or watched his material when learning machine learning, including myself. The most important thing today is he is also a student of Machine Learning Summer School 2006. After 15 years, today he joined Machine Learning Summer School again with a different role. Today, he will give us a very inspiring topic called sensitive classification, techniques, and story. Let's welcome Professor Hsuan-Tien Lin.
Okay, thank you, Hong-Yi, for the very nice introduction. And he actually covered many of the things that I want to talk about in the beginning. And it's a great honor to be in Machine Learning Summer School this year. And Hong-Yi mentioned about the book that I co-authored and the MOOCs that I taught. So I'll talk a little bit more about what my lab is doing or what my research goal is. Basically, what we try to do is to make machine learning more realistic. And all the research that we have done surrounds this theme. So in recent years, you see our lab publishing things like in weekly supervised learning, in online and active learning in top conferences. And those are efforts to make machine learning more realistic in terms of collecting data using weaker data to achieve decent learning performance. And Hong-Yi mentioned our achievements in KDD Cup, and that was our attempt to understand the real world problems more to help actually using machine learning as the core tool to solve those problems. And the topic that I'm going to talk about today surrounds 2 other topics that my lab has worked on. One is on cost-sensitive classification, and the other is on multi-label classification. And we will see that we combine the concepts, the 2 concepts together in the second part of this lecture. And as Hong-Yi mentioned, okay, I'm very happy to be returning to Machine Learning Summer School as a lecturer because 15 years ago, this was me. Okay, actually, this is the video that's found on videolecture.net. That was the video recorded during Machine Learning Summer School in Taipei at 2006. And at that time, I was a PhD student at Caltech. And I went back to Taiwan to attend Machine Learning Summer School, present this work, which strongly influenced how I shape my PhD thesis. This becomes a very critical part of my PhD thesis, and I surely enjoyed the experience. So I really encourage everyone here, every student here, to take this opportunity to know more people, to know more technical details, to present your works in poster sessions and so on, to have a wonderful experience here at Machine Learning Summer School, Taipei. And before I start talking about the cost-sensitive classification today, I want to provide some disclaimers. Okay, first, I've given tutorials on cost-sensitive classification twice. Okay, once in 2013 at ACML, and the other 2 years ago at KDD. So this is more or less the third time that I give a tutorial or give a lecture on cost-sensitive classification. And if you have watched those materials, you will find that many of the contents that we'll talk about today are mostly old. But after discussing with the organizers, we find that these materials may still be useful for this community, although the core techniques are mature. But we actually see new research works, inspired by those cost-sensitive works in recent years. For example, ICML was just a few weeks ago, and I saw one very interesting work from Japan talking about linking cost-sensitive classification to classification with rejection, which is a new problem setting, that's more realistic. And also in ICLR, we saw some works related to cost-sensitive classification. So knowing how those techniques are in the literature should still help you to think about how to use them properly or how to extend them for your own research work. And also, in addition to the techniques that I'm going to talk about today, I will share with you one application story that I had for cost-sensitive classification, which should provide some insight about whether what we're discussing here or what we're doing as machine learning researchers really help making machine learning more realistic. So that's the plan. Techniques, those mature ones to prepare for your background to link to your own research, and the story to help you think about how to connect your research to the real world. Let's begin. In the first part, I'm going to talk about cost-sensitive multi-class classification. And let's do the setup first. Let's start with a very traditional machine learning problem. I write a digit, and I want the machine to recognize which digit that I wrote. So digit recognition problem. And if you are using some of the mature deep learning data sets, maybe USPS or whatever, you will recognize that this is exactly the problem when people begin to push machine learning to the real world for the optical character recognition problem. And we are presenting a simplified version here. Let's say we only have 4 digits, in the world, 1, 2, 3, 4. So you'll recognize that this is a typical multi-class classification problem. We're grouping the pictures to different categories. And you'll say, come on, Professor Lin, we know all too much about multi-class classification. This is machine learning summer school. Present us something more advanced and so on. Bear with me. This is just setting up the tone. Let's ask one question. How should we evaluate the performance of multi-class classifiers? I mentioned about digit recognition. Actually, in the very beginning, it was zip code recognition. In the zip code recognition problem, you can say, so in these 4 cases, if the machine predicts correctly, we say, oh, great, you're correct. And in all the other 3 cases, the machine made a mistake. So there's only right or wrong in the usual zip code recognition problem. Let's say we're moving this classifier to be used in check value recognition. Then the situation is a bit different. Still people are writing digit and we want the machines to recognize the digits correctly, but different kinds of mistake may mean different kinds of monetary loss, depending on whether you're standing on the side of the bank or the user, but let's take the absolute value. So if the prediction is 1 or 3, it's a $1 mistake, but if the prediction is 4, then the error amount is different, it's a $2 mistake instead of a $1 mistake. And therefore, we may want the machine to take these different kinds of mistakes differently when preparing the classifier. So we use this example to highlight that for different applications, actually, we may want to evaluate the mispredictions from the classifiers differently. And that's what motivates us to study cost-sensitive classification. Cost-sensitive, the cost actually means how we do the evaluation. and we want the machine to take the evaluation criteria into account. Okay, so the original problem, the original multi-class problem that we discussed with only two kinds of outcomes, correct or incorrect, or right or wrong, is usually called regular multi-class classification. And we can formulate it mathematically as follows. Okay, we can say in the right case, in the correct case, the cost is 0. Okay, we will charge the machine with 0 penalty. But for the wrong case, we'll charge the machine with a penalty, a cost of 1. And this is called the classification cost. You should be familiar with that. Okay, it evaluates whether the label, the Y that we want is the same as the prediction, h of x. We are using the usual machine learning formulation, whether it's the same or not. Okay, if the same, 0. If it's different, then 1. Okay, I'm using this square bracket for the Boolean notation here. And this regular multi-class classification problem is the one that you often see in literature. It's well studied. There are many good algorithms ranging from decision trees to SVM to deep learning, and you all know very well about that. How about trick value recognition? Well, this is what we call cost-sensitive multi-class classification, in which we assign different costs for different kinds of misprediction errors. For example, in this particular case, we're actually using the absolute cost to evaluate our classifier, evaluate our algorithm. And this absolute cost measures the absolute difference between the prediction and the desired label. And we'll tell you more about cost-sensitive multi-class classification, or we call CSMC, here in the first part of the lecture. Now, let me provide one more motivating example. Okay, let's say we're trying to evaluate the status of a patient in a computer-aided diagnosis system. And let's say the patient has 3 different kinds of status: healthy, regular cold, or bird flu. Or if you want, you can even put in more serious things like COVID-19 or something. But let's not scare ourselves. Let's just have 3 cases here: healthy, cold, and bird flu. And this is another classification problem, as you can see. And what we want to ask ourselves is, are all misprediction costs equal? If you think about it, maybe the answer is no, in terms of the society cost. As we all know, bird flu is a more severe disease in terms of transmission and society cost and so on. So if the patient actually has a bird flu, but is predicted by a computer system as healthy, then the patient would feel healthy happily and go out, maybe not wearing a mask or anything, and basically pass the disease to lots of other people, causing the society a big cost. And I'm putting the big cost as 100,000 here, just as an illustration of how serious this kind of error is. So if bird flu mispredicted as healthy, it's a mistake, and it's a huge cost mistake. How about for regular cold? Well, we get cold occasionally. So if a regular cold is predicted as healthy, yes, the patient with the cold status may pass the disease to more people and so on, but it's a less serious mistake. Of course, we want the machines to be correct. We want the machines to make correct predictions, like in the diagonal, the green cases here, where a bird flu infected patient is correctly predicted as cold flu infected, and a healthy patient is predicted as healthy. But that's not always the case. The machines make errors, You know it, I know it, We work on machine learning. We know that the machines are not perfect. They make mistakes. But different mistakes seem to have different costs, at least for this problem. And if you go to a human doctor, every human doctor would have this kind of cost table built inside her or his brain. Okay, so basically number may be different. Okay, but in terms of the seriousness, okay, the doctor may have a sense that, okay, this may be a very serious mistake, this may be a less serious one. So the doctor would pay attention to the slightest bird flu symptom. Okay, so to prevent the doctor from making the super big mistake. Then, if we were to develop a computer-aided diagnosis system to help the doctors, we need the system to also have this kind of table built within its brain, so it can make decisions more similar to the doctor's needs. Okay, we don't want the system to easily make big mistakes. That's the motivation of this line of cost-sensitive classification, this cost-sensitive multi-class classification research. Oh, by the way, the organizers told me that you may ask questions during the lectures, and that's totally fine with me. So what I generally do is for every few slides, I'll switch to the chat panel, okay, and check if there are questions there and answer them immediately. I believe it's the best mode, so to keep everyone on the same page so we can keep the best learning performance throughout this lecture. Okay, so if you have any questions on any of the slides, please feel free to paste them in the interactive chat box, and the organizers will try to pass them to me during the lecture. Okay. Now let's go to some more formal setups that we will use in this lecture. Okay, we will take the usual machine learning notation, the supervised learning notation that we have big N examples. Okay, and each example is composed of the input part, okay, like the pictures that we see, and the label part, okay, the class that we want the machine to classify to. The number of classes will be denoted big K, and in the first cost-sensitive classification setup that we will introduce, we assume a cost matrix, okay, where this cost matrix actually tells us the seriousness of each kind of mistake. Each row of the cost matrix, okay, actually means the actual label, the ideal label that we want, and each column would mean the predicted label. Okay, so this is the cost table, the cost matrix that we had for the patient classification case. And in the diagonal elements of this cost matrix, we will assume to have all the values being 0, which is the minimum within each column, okay, indicating the best choice or the most correct choice. Okay, and for the check digit recognition problem, we can even represent the cost matrix more concisely with a function. And our goal is a classifier that pays a small cost on future unseen examples. Okay, so for any future example, we ask the machine to make the prediction and then compare it with the ideal label using the corresponding entry within the cost matrix. Okay, and that's the evaluation that we're going to take. And this setup includes the regular classification as a special case. Okay, so you can think of this as a generalization from regular classification to more general cases, to anything with arbitrary cost matrices. Okay, I'm going to highlight another example, which was actually the motivating case that inspired me to study this problem. And this was part of my PhD thesis and part of the presentation that I used 15 years ago. Okay, so 15 years ago, this was kind of how I got started. Okay, and we were trying to solve a very special classification problem that predicts the age group, okay, of the person in the picture. And let's say we have 4 age groups. As you see, these age groups labels are not the usual classification labels. They have a property that they are ordered. And because they are ordered, there are smaller mistakes and bigger mistakes. Okay? Bigger mistakes when you are predicting a class far away. Okay? And smaller mistakes if the predicted class is wrong, but things are nearby. So this kind of ordering can also be represented as a special cost matrix, okay, where each row of the matrix would be somewhat V-shaped, okay, where the value of the V would be in the diagonal part, and for two other sides of the prediction, it would follow a monotonic order. Okay, so this is the kind of cost matrix that can embed the intent of ordering the labels. And this is called the ordinal regression problem or the ordinal ranking problem that was the main part of my PhD thesis. And this is how cost-sensitive multi-class classification can help, okay, as a possible way to solve this kind of ordinal ranking problem. And actually, I know in the morning you had a great lecture on reinforcement learning. And if you think about it, in reinforcement learning, if you have a finite number of actions, okay, in each horizon, it actually means you are doing a classification problem in some sense. And the reward that you get, okay, serve as the negative cost. Although you are in reinforcement learning or embedded learning, you're having something different that you're only getting partial information. But in an essence, okay, every choice that you have is attached to a different cost or a different reward, and you are trying to maximize the reward or minimize the cost. And that's also a strong connection between cost-sensitive classification and bandit or reinforcement learning. And so this is something that you can think about. Okay, this kind of cost-sensitive view actually exists not just for supervised machine learning problems, but for also some other types of machine learning problems as well. Okay, so we talked about the cost matrix setting, and I'm going to extend it more generally to another setting that's called a cost vector setting. Actually, the cost vector setting connects even more closely to bandit and reinforcement learning, where in each iteration of your online learning process, the bandit or reinforcement learning process, you are actually observing part of a cost vector. A cost vector from the cost matrix view is just one row of the cost matrix. So for example, for the bird flu infected patients, the cost vector for her or him is just one particular row, okay, indicating how we are going to evaluate its performance. And for digit 2, the absolute cost, we can evaluate it and form a vector like this. And this kind of vectorized formulation allows us to actually attach different vectors for different person, okay, different examples. Okay, so we're no longer needed to bind to a particular matrix or a particular function, but what we can do is to be very personalized. For example, in a recommendation system, let's say there's someone who loves a romance movie but hates terror. Then the cost vector for this user may be, okay, predicting romance, fine, okay. But if the prediction is terror, then it can be seriously wrong. Or for someone who loves both romance and terror, maybe a wrong prediction is not that serious, okay, as basically we can still recommend a good romance or terror movie to her or him with good satisfaction. Okay, so basically a cost vector setting allows us to be more fine-grained in assigning the costs in particular problems. And for the cost vector setup, what we can replace is really, okay, we have inputs, we have labels, but for the cost matrix part, we no longer have a global cost matrix that indicates the cost. But now we have local cost vectors per example. Okay, each cost vector would still satisfy the property for indicating the correct label. And in this case, we need theynth component of the cost vector to be 0 to represent the minimum cost. And our goal is a classifier that pays a small cost for future examples. And for these future examples, we assume that the input is given and the cost vector is given. And we will be using this to evaluate the future examples. And in this setup, you can see that we don't really need Y. Okay, for the matrix setup, we need Y because Y is used to look up the corresponding row in the cost matrix. But for the cost vector setting, it's a more general setting. We just need to assume that we have generated X and C on hand and use that to do the learning, to do the evaluation. And Y is supplementary, but not necessary, or we can derive all the information we need about Y from the cost vector, okay, given our assumption of the cost property here. So in this sense, we can see that, okay, we talk about regular classification. If you extend it, you get class dependent, okay, the cost matrix one, the class dependent cost sensitive classification. And now this one is example dependent. Okay, every example carries its own cost vector to be learned from. Okay, so these are the setup that we're going to talk about today. Okay. Now I see some good questions here in the chat, so let me answer them first. First, is cost-sensitive classification related to base risk and minimax risk? That's a very good question, and actually we will answer this question probably 3 or 4 slides later, okay, in my very first topic. Okay, so how cost-sensitive classification can be solved from a Bayesian perspective. Okay, the second one, do we always assume that the cost matrix is known a priori? Okay, or sometimes we may not be able to quantify the matrix exactly. Okay, and that's a very good question as well. Actually, we see some extended work that tries to tune the cost matrix towards the needs. Okay, so indeed, we can consider a more general problem where the cost matrix can keep changing, or the cost vector can keep changing to fit the application needs. Actually, one of the good view to look at cost-sensitive classification is that it provides some more tunable knobs to the machine. Okay, for example, some of you may know weighted classification. Okay, we're very used to adjusting the weights of different classes, especially when we have imbalanced classes or imbalanced number of examples, and we tune the weights so that we get better performance. Now, similarly, we can use this cost matrix to tune for better machine learning performance towards our needs. And I will try to introduce some of the thoughts along that direction near the end of this lecture. Okay, and indeed, it is a very important problem. Okay, and if I understand correctly, to use cost-sensitive multiclass on a particular problem, you will need knowledge from experts of that field in order to assign different costs for the misprediction, right? Or this is not needed and be inferred from public data sets, okay? And again, very good question. In the very last part of the story, this is actually one of the issues that we need to discuss. Where does this cost come from? Okay, how do we get these costs, and whether we can do better or not, okay, with or without the exact cost information. Okay, that's something we will discuss more. And I'll remember to talk more about that when we learn about the techniques. But for now, let's say this. Okay, we are making a strong assumption that we know the costs, and we want to do better with respect to these costs. And yes, when you are connecting this assumption to the practical world, there are all kinds of things like where the cost comes from, whether the cost is exact, whether the cost is adaptive, and so on. And those are very valid questions if you want to put things to practice. But for techniques, okay, let's be purists for a while and say, okay, we have the cost, how can we do well? And then we talk about how to solve the other challenges. Okay, would you agree that if we implemented cost-sensitive classification in social credit system, it would have been an improvement? Okay, should we highlight a sample when their total cost is higher or their highest cost is higher? Okay, that's a very interesting question. Okay, being in the question, there are two evaluations. Okay, one is measuring based on the total cost. Okay, and this is a simpler setting that's closer to what we're discussing here, saying, okay, we are evaluating the cost on each example and we're summing it, okay, the total cost in some sense to evaluate the performance. While in some systems, it may not be that simple. For example, this participant told us that maybe we should evaluate in terms of the highest cost, okay, the most serious, the most erroneous case, okay, rather than the sum or the average. That's certainly possible, but this kind of evaluation function is actually more complicated than the cost setting that we're discussing here. When things are more complicated, what should we do? We should learn how to do those simple stuff first, and then use those simple stuff to tune for better classification in the sophisticated scenario. And that's connect to what the other audience is asking, whether we can modify the cost metrics to tune for better performance. Okay, so this sophisticated one, not the one we're discussing, but we can use what we're discussing as the tool to do better in the more sophisticated cases. Is it possible to apply any loss function and consider the probability output of the multiple cases while considering the costs as well? Okay, it's certainly possible, okay, but as we will see later, what's the other loss function can cause us is that it can be time consuming to infer which prediction is the best choice. And also, okay, I'll hint you for now, the procedure for taking a good probability output is actually non-trivial. Okay, it's not that easy to get a probability output anyway. And if we cannot get a good probability output, then it would be very hard to get good cost-sensitive decisions. And that will be talked about in the very first part of my lecture next. Okay, great. Thank you for many interesting questions that you have. Let's move to the Bayesian part, okay, where many of you seem to be super interested. Okay, in the Bayesian part, as some of you suggested, we will call for the help of a conditional probability estimator. Our goal in a class-dependent setup is a classifier that pays a small cost. Then, if we actually know the underlying conditional probability distribution, okay, we can get the base optimal decision to be just evaluating all the possible cases, okay, gets the expected cost for every prediction, okay, for every possible label, and then just picks the one with the smallest expected error, the smallest expected cost, actually. So that's the base optimal decision as we know it. Now, we don't have the conditional probability on hand. What should we do? So I call it approximate. If we can get a good approximate conditional probability estimator, okay, then we can just use this estimator, I call it Q here, to replace the P that we see on the left-hand side to form a good classification rule. Okay. If we can form a good Q, then we can form a good G, where G is our actual classifier, and Q is just the intermediate conditional probability estimator that we use. How do we get a good conditional probability estimator? Well, you know many of the cases, right? From your machine learning class, your basic machine learning classes, okay, you know logistic regression, we can do that naive ways, we can do that. Okay, there are lots of ways to do a good estimate of conditional probability. And this was the work back in 1999 when people started doing cost-sensitive multi-class classification. And I named it, actually at that time they didn't have a good name for that, and I named it ABOD, Approximate Base Optimal Decision. Basically, the idea is simple: get a good estimator, replace the conditional probability term in the base optimal decision with the estimator. And in this approach, okay, you just use whatever your favorite algorithm is, and then in the end, you make the final prediction. Probability estimate based optimal decision. I believe this can be one of the very first solutions that many of you think about if you were to solve this problem. Let's see how it works, okay? In this particular data set, I'm using logistic regression to learn the conditional probability of each case, okay? And you can see from the left-hand side, this is the data sets that I provide to the machines, a 2D data set with 4 classes indicated by 4 different symbols. I'm using logistic regression to learn from this data set to get a good or an okay conditional probability estimate. Actually, I think I'm using 1 versus all logistic regression, and you can see some slight color difference. Okay? Not a super strong one, but you roughly see that okay, in different regions, the colors are slightly different. Now, if I couple this result learned from logistic regression with a cost matrix that you see here. I'm calling this a rotate cost matrix because this cost matrix is particularly designed that if you predict the class in a counter in a class clockwise manner, predict the next class, you suffer from a smaller cost than if you predict the class to a counterclockwise manner. Okay, so you see that there's a symmetry between your next class and your previous class in terms of a class-wise manner. So if I plug in this cost, you see that the decision boundary is somewhat like this shape. While if I don't plug in this cost and I use the usual logistic regression, the 1 versus all decision rule to form the decision boundary, this is what we get. Okay, so the regular boundary, is more like a square region for the 4 classes and so on. But once we plug in the cost, the effect to predict the safer class, give a rotation effect of the decision boundary. And this is what we can do with ABOD, with approximate base optimal decision. Now, for binary classification, we can do the same. Actually, for binary classification, if you think about it, your whole cost matrix would simplify to 2 weights. One for false positive and one for false negative. You just have 2 values of freedom. And let's see how things go. If we have a conditional probability estimator that estimates the probability of being in the positive class, then the decision should evaluate, whether it's safer to predict the positive class or safer to predict the negative class based on this. And we can simplify this decision rule. Actually, it can be traced back to a work in 2001, and to say, if we're evaluating those 2, when should we predict positive? We should predict positive only if the positive probability is greater than this ratio that can be computed from the weights. So these weights, these costs, tell us how we should shift our decision boundary, to have cost-sensitive decisions. So this is very simple to derive. And this binary classification case actually simplifies to just threshold changing. Not the complicated rules that you see in the multi-class case, but now you can just do threshold changing. So similarly, if we evaluate the performance of this on a binary classification data, and this is what we get with logistic regression. This boundary that we get, if we have the false negative, being 10 times more expensive, then the whole decision will be shifting, towards the negative side. We will have a bigger margin on the positive side. While if we don't plug in any cost, then the decision boundary will be somewhat in the center. So I'm hoping that this illustrated examples shows you something about how cost-sensitive classification is changing the decision boundary towards better matching our needs. Now, what are the pros and cons of this approach? Okay, we say that it's derived from Bayes optimal solution. So if we have a good probability estimate, or if we have the best probability estimate, then it should be optimal. And this prediction easily adapts to different cost matrices without modifying training. In training, you only have probability estimate, no more, no less. Okay, but in testing, you can use different costs, okay, and to change your decision boundary to fit your needs. How about cons? Okay, I hinted that it's difficult to get a good probability estimate. Okay, it's usually more difficult than getting a classifier. You get a classifier, you don't need to worry about whether the probability values are accurate or not. But for probability estimate, you really need the values to be somewhat accurate, and it can be difficult. And also it's restricted, because in the decision making, you need to understand the full trade-off within the cost matrix to form the decision. Okay, and therefore, we can only use this approach in the class-dependent setup, not the example-dependent setup, which is more general. And also, although the training part is faster, the prediction part is slower, especially if you have many classes, right? If you have many classes, you are essentially doing matrix value multiplication and some operations per example, and it can be time-consuming. Now you may ask, okay, then have people tried to develop approaches, okay, that uses any multi-class classification algorithm for ABOD, okay, rather than relying on probability estimates? And the short answer is yes. Okay, again, it's back to 1999, the very first multi-class cost-sensitive classification approach. What it does is basically replacing the probability estimate step, okay, using bootstrapping, okay, much like what you do in bagging, but for this bagging, you are getting the result and use the voting to get your probability estimate. Then after you get the probability estimate, okay, you do another step. This other step is called relabeling. So basically, per example, you try to calculate its approximate Bayes optimal decision, and then use this decision to relabel your training data. Why do we relabel the training data? Because we want to escape when the time-consuming step when making the prediction. Okay, we don't want the prediction to keep carrying the cost matrix. And after relabeling, you can just retrain with your favorite multi-class classification algorithm. So this relabel data should carry the ideal cost information that we want the machine to digest. So then any multi-class classification algorithm can be used to digest the information and get a cost-sensitive classifier. That's called the meta-cost approach. Okay, so basically, two-step approach, reusing your favorite multi-class classification algorithm. First step, getting a probability estimate. Second step, retrain on a relabel dataset. Okay, and the good thing about this algorithm is that any multi-class classification algorithm can be used. And we can check its performance here. This is actually Megacost coupled with C4.5, which is the popular decision tree algorithm as you know it. Okay, and this figure is done on some artificial data sets, okay, generated with UCI data. So data sets are UCI, okay, but cost metrics are randomly generated. And here on the horizontal axis, okay, it shows the performance of the Megacost algorithm. On the vertical axis, it shows the performance of the original C4.5. So horizontal, okay, basically saying it's cost sensitive. Vertical, regular. Okay. And there are many different data sets that the authors tested, some multi-class, some two-class, each one represented by a point on this 2D plan. And the dotted line, okay, represents equal performance between the two algorithms. And because we're caring about costs, okay, the lower, the better. So basically, if you check the upper left part, okay, those are the parts that cost-sensitive classification better, and C4.5, the regular classification, worse, okay, suffering higher cost. And you see many of the points falling into the region on the top left side, okay, which tells us that this meta-cost algorithm really works, considering the cost properly does help in this cost-sensitive scenario. Okay, so let's summarize the first part of multi-class cost-sensitive classification using a base perspective. We started from approximate perspective covering both multi-class and binary classification. Then we try to escape, okay, the use of probability estimate by using a multi-class classification algorithm instead. Now, okay, let me check whether there are more questions here. Okay, is there an optimal strategy for relabeling the training examples for faster convergence? Thanks for this question. Actually, we will tell you something about some more theoretically grounded relabeling strategy. Okay, but then I'll also tell you that it may not lead to faster convergence. Okay, it represents better information, but not necessarily for faster convergence. And in my experience, I don't know, okay, whether there are related results for relabeling for faster convergence. But we can discuss more about how theoretically we should do the relabeling. Are there any way when the cost matrix is unknown, we can serve the cost matrix as parameters in the model so machine can tell what's the best cost matrix it thinks? Yes, okay, the short answer is yes. And actually, my student had to work a few years ago on this. Basically, we're trying to tune the cost matrix towards better imbalanced learning performance. So this is certainly doable, okay, but relies on, I think, more research, okay, to be mature. So basically, if you think about this cost matrix here as the tool you can use, I do believe there's potential to tune, okay, this tool towards matching whatever sophisticated cost function that you want to solve. How does ABOD compare to Megacost? Okay, that's a good question. I didn't make the comparison. Okay, that's one thing. ABOD and Megacost are proposed in the same paper, and Megacost is the actual algorithm that the author Pedro Domingos proposed, and ABOD is kind of like intermediate. So I don't specifically remember whether there was a comparison in the paper, but my guess was not, because Megacost was meant to design for reusing, okay, existing multi-class classification. And for comparing Megacost with ABOD fairly, it could rely on very careful tuning of, okay, whether we have a good probability estimate, whether we have a good multi-class classification, and so on. So the comparison is not that easy. And in Megacost perspective, it's just a special case of ABOD. Okay, so even if Megacost does better, it just means ABOD can do better, okay, but it requires some more tuning, particularly towards the probability estimate side. Okay, this question, this might be a little off topic. Are there any connections between cost-sensitive multi-class classification and self-paced learning? Thank you. Okay, as some of the other students asked, it is possible, okay, to tune the cost matrix towards some sophisticated criteria of the interest. And in this sense, actually, I believe there's a potential to introduce self-paced learning into the picture, okay, thinking about what's the pace in terms of tuning or learning the cost matrix, okay, and that's an interesting direction, but we haven't seen many works towards that direction. But I personally believe it's a very interesting idea. Unfortunately, none of my students were persuaded to do that yet, so we'll see. Is the cost matrix human defined? Is there some research to train a cost matrix? Yes, there are some research to train a cost matrix, but not that many yet. And for here, we're talking about a cost matrix that's given. Okay, whether that given is human defined or given from other sources, we don't care that much. Okay, we only assume it to be given. Okay, great. Thanks for the many questions. And I believe we need to move a little bit faster if we were to finish all the stories that I prepared to talk about. Let's do this. I know we've been running for 15 minutes now, but let me finish one more topic, answer all the questions before we take a break, so we can try to be on time. Okay. Now we talked about relatability. Okay, in the Megacost algorithm, and some of you noticed that the relabeling is somewhat heuristic. Okay, and here we are asking whether we can do it in a more principled way. Okay, how do we do it in a more principled way? One way to do that is to observe the cost of interest has some shift equivalence. Okay, if we add a constant to every component of the cost matrix, then basically the optimal prediction is the same. Okay, it's much like you add a reward or decrease a reward in reinforcement learning, okay, like what you do in reward shaping and so on. Okay, so basically, if that there's a constant to be added to every component of the cost vector, then the optimal prediction is the same. The optimal decision is the same. We call this the shift equivalence. And with this shift equivalence, we can derive a relationship between the shifted cost that I list here and the regular cost matrix. Remember, we said regular classification is just a special case of cost-sensitive classification. So the intent of regular classification can be represented as a cost matrix as well. And why do I use this matrix formula to connect the two? Okay, I'm interested in the shifted cost. I want to connect to the regular cost. Because this connection, actually, those coefficients here for the connection, this 1, 2, 1, 0 here, actually reweights each row of the cost matrix. Right? Okay, each component here, this 1, 2, 1, 0, each one can be used for reweighting the row. And this reweighting the row actually tells us we should put more emphasis on different rows of the cost matrix as if we have relabeled data from each row. Okay, so this is the connection. The original cost vector of interest is equivalent to a weighted mixture where the weighted mixture contains relabeled examples along with different weights. So I have X, I have Y, which are relabeled, and I have this U, which are the relabeling weights. And you can see that it puts more weights on the second row. The second row is our original best label, but it gives some weights on some good rows as well. Okay, the good rows are the ones that suffer from small costs only. Okay, so the weights represents our intent to represent different costs, and this was what I derived in my PhD thesis. Actually, basically, we're connecting the cost vector of interest to a weighted 0-1 error, and this weighted 0-1 error tells us that we can just relabel our data according to this mixture and the total weights. Okay, the total weights of what we have done wrong for this weighted mixture would tell us equivalently what our original cost is. And if we minimize the expected right-hand side, which is what we can do with usual weighted classification. Okay, weighted classification, I assume you are familiar with that. We take the examples, we add the weights to our optimization formulation, and we get the classifier like what we do in usual multiclass classification. Then we can solve what we want on the left-hand side, which is the original cost-sensitive multiclass classification problem. And there are infinite number of ways to do the transform. Okay, I'm skipping the math details and just tell you that, okay, there's one way to find the smallest non-negative values, because we need non-negative values to actually serve as the mixture weights. Okay, one way to find the non-negative mixture value is really to take the largest cost component and use it to deduct every cost component to get the mixture weights. So that's what we saw. Okay, the largest cost would be the least preferred label, which would have 0 weight in the mixture, and the smallest cost would have the largest weight in the mixture because it's the most preferred label. So those weights, those mixtures, embed the cost that we want, okay, in a principled way, okay, relabel and mixture. And this is actually called the Dataspace Extension approach that was developed much earlier in the literature in 2004. And in this work, what they try to do is for each example, we calculate the weights, we relabel our example, actually we mix all the examples, okay, in as a super big training set, and then feed it to our multi-class classification algorithm to get the classifier, and it is called Dataspace Extension. By the cost equivalence theorem that we derived, a good classifier for the new problem is a good classifier for the original cost-sensitive problem, and this weighted one is not that hard to solve. You can use sampling. You can modify the objective function. You can use lots of different approaches to get a good weighted classification classifier. Okay, so anything can be used. And in the work in 2004, they actually compared it with Megacost, and they used the sampling approach to implement weighted classification. And this was the results that they get. On the horizontal axis, there are 5 data sets. On the vertical axis, it's average test costs. Megacost, the red one, okay, and Dataspace Extension, the blue one, okay, because we are evaluating the average test costs, the lower, the better. Now you can see that the results seems to be competitive. On the first 3 data sets, Megacosts are better. In the last 2 data sets, Dataspace Extension looks better. So at best, we say it's competitive. Okay, it's not really better or worse, at least for the results from that paper. And actually, additional research along this direction found that the DSE approach has some disadvantage. The disadvantage is that this relabeling process actually introduces noise to the dataset. I'm illustrating it with this 2D example here. We see that we have 4 classes of data, no noise. Okay, so you see cleanly that these 4 classes, there's a boundary and everything cleanly between the different classes. But if we couple this with the absolute cost, so the absolute cost would tell us we need to do some relabeling with the mixture and reweighting of the sum of the classes, and I'm using different sizes of points for the reweighting, and I'm using sampling, okay, to represent the possibility of landing into different kinds of relabels. And this is the data set you get, or this is the data set you feed to the machine learning algorithm if you use the DSE-like approach. So you see, we're kind of using noise to embed the cost information. Okay, we want the machine to know the cost information, but we are embedding it in a way that's not very friendly to the machines. We're embedding it with noise, and we know that machines generally do not do very well under noise. And that's one problem of this DSE approach. And that is the new problem, the new classification problem is usually much harder than the original one because of this noise. And we can only solve the new problem well with robust multi-class classification algorithms. We need to design robust ones, okay, not just any usual one for multi-class classification in order for DSE kind of approach to do well. And one attempt that people had, actually I had when designing those algorithms, is to use 1 versus 1 comparison for multi-class classification, because in 1 versus 1 comparison, we're zooming into only 2 particular classes, okay, and we're using voting in the end to eliminate the noisy predictions. If we couple the 1 versus 1 approach with Dataspace Extension that we just mentioned, we can simplify this to a very simple algorithm. 1 versus 1 comparing 2 classes. And actually, we are just checking, okay, each example, whether it favors one class or the other. Okay. And within that binary classifier, we just need to use, okay, which cost is higher, and then use the weight difference, okay, to indicate the importance of this example. And this is kind of unshifting. Okay, so comparing only 2 of the classes, their weights can both be of positive value, but we're shifting it down 1 to 0, the other to a positive value, so we can remove the noise, okay, in when comparing those 2 classes only. And this robust step makes it suitable for Dataspace Extension kind of algorithms. And this is named the cost-sensitive 1 versus 1 algorithm. It's basically combining the DSE that you saw with a robust extension of the 1 versus 1 algorithm that you usually see. And this algorithm actually has some theoretical guarantee that I'm going to skip here. Basically, it says if each binary classifier does well in terms of the test cost, then the final voting classifier would also do well. It is a sibling of another approach called weighted all pairs. And that approach enjoys a tighter theoretical guarantee, okay, but its construction is actually more sophisticated. And the physical meaning of each binary classifier is that it answers a yes-no question of whether we prefer class I or class J on that particular example. Let's see some experiments. Okay, this is CS-OVO versus OVO. So OVO is just the original 1 versus 1, no cost. CS-OVO with cost. CS-OVO is in blue, OVO is in red. And on the horizontal axis, 6 different data sets. On the vertical axis, average test cost. So the lower, the better. We can see that in most of the cases, okay, actually the one with cost can lead to better performance. The blue bar is lower. The only exception may be in the val class. So considering the cost properly does help, okay? Not surprisingly, just like the results that we saw in the meta class case. And if we move the scenario to ordinal classification, ordinal regression that we introduced earlier for age group prediction kinds of data, the difference is actually more significant. And that's because we're using the cost to take the ordering probability into account. Now, this CS-OVO algorithm has some disadvantages. It takes many binary classifiers to form its decision because it's essentially taking a tournament comparison between all the different classes. It's time consuming to train, okay? Because in training, we are in each classifier, we're actually using all examples for comparison and with all K-2 binary classifiers. And it's time consuming to predict because we need to take all the classifiers and do the voting and so on, okay? But generally, it's not feasible for large K. Now, can we do better? Well, one possibility to do better is Olympic time. So I assume many of you are watching the Olympics game, and you can think, okay, the reason that we're not running Olympic game for 2 months, okay, is because in the tournaments, okay, in the competitions, they're actually using some sort of elimination tournaments rather than just round robin. Okay, round robin is like 1 versus all, but for tournaments, okay, we can have 2 teams competing with each other and eliminate some of the teams, okay, so we can reach the conclusion we can get the champion faster. So the prediction task is just like deciding a tournament winner. And if, okay, we use single elimination kind of tournaments, okay, then we can, in the real world, we can have K-1 games. Okay? We can just play K-1 different games, okay, to get the final prediction. And actually, for computers, it's even faster. If you use this kind of tournament elimination, and when doing prediction, you can actually ask the questions in a top-down manner. Then it's just like searching within a binary tree, and you can use log K games, okay, for predicting which class is the winner. And next, we'll talk about a single elimination tournament for a cost-sensitive multi-class classification. But before that, let me move to Q&A to see if there are additional questions. Okay, could you provide a high-level intuition on why Megacost should work? The intuition for Megacost is really, it's basically it's a case of ABOD. Okay, so from the Bayesian perspective, if your probability estimate makes sense, then your prediction makes sense. Okay, so now assuming you can use multi-class classification to get a good probability estimate, which in Bayesian style approaches, okay, people seem to have found so. Okay, so the estimation should be pretty good. Okay, then the relabeling helps you to get a data set that's particularly strong for cost-sensitive classification that embeds the cost information. So the high-level picture is that the two steps makes proper use of multi-class classification to get good performance. What are the properties of the data sets that might determine whether DSE would work better or Megacost? The short answer is I don't know. Okay, or at least I haven't seen the literature on which would work better for what. My guess is that Megacost heavily relies on probability estimate. Okay, so if we have enough examples such that bootstrapping can help us make good probability estimate, then Megacost might do better. While DSE heavily relies on the robustness of the underlying multi-class classification algorithm. So if the multi-class classification algorithm is more robust towards noise, then DSE might have some advantage. But since their strengths are on very, very different kind of learners, okay, I believe it's really hard to make a fair comparison, whether data set wise or algorithm wise, to compare their performance. Okay, great. Thank you for your questions. To be honest, I'm a little bit exhausted, so let's take a 7-minute break. Okay, on my computer, it's 8 minutes past 4 now. So let's go back 15 minutes, a quarter past 4. Okay, so we can continue with the rest of the lecture. Okay, and in the meantime, please feel free to ask more questions in the chat box so I can answer them later when we come back to the lecture. Okay, thank you for your attention. Let's take an 8-minute break before we come back. Thank you. Okay, hello, welcome back to our lecture here. And in the previous parts, we talked about cost-sensitive multi-class classification and how the one versus one kind of approach that we just learned can be viewed as round-robin tournament. And now we're going to learn another algorithm that's based on single elimination tournament. And before we do that, let me answer one question that we saw in the chat channel. For weighted cost classification, how can we detect overfitting in our algorithm, or how do we select the weight? Is it by trial and error, or is there a more structured approach? Okay, let's separate this problem to separate parts. Okay, first is cost. Okay, so basically, if you look at a cost-sensitive classification problem, then cost is your parameter, and as any parameter that you can have in your machine learning algorithm, you need to select the parameters to ensure the best performance. And generally, you do the selection much like what you would do with other parameters, like learning rate and so on. You set up a proper validation and use that validation to see whether you are making true improvements or it's just overfitting. Okay, so that's the part if you can use cost as a parameter to tune your algorithm. And if, okay, you have this view of using costs as parameters, then when costs are transformed to the weights, okay, that we discussed in, for example, DSE or weights, there are automatically calculated, at least in principle, from the algorithm. Okay, so you have the cost there that you use corresponding weights. Those can be computed automatically by the algorithm. And that's the bigger picture that we're discussing here. Okay, so let's look at the tournaments. And in this filter tree algorithm that's back in 2009, there's a bottom-up. So for each example, we view each node of the tree as a classifier that tries to put each example into the correct class. So each leaf of the tree is represents one class. And then each example can be used to build the comparison, the binary comparisons. Let's look in more detail. For example, let's look at this G hat 1, 2 here. So it's comparing class 1 versus class 2. Which one is more preferred? We can ask each example which one is more preferred, just like what we do in CSOVO. 1 versus 1 comparison. Okay, 1 or 2, which has a lower cost. So each example can be converted to one such binary case. Okay, so basically telling the classifier whether the better choice is to walk left or to walk right. And what's the difference of the choice, right? Okay, for example, for this particular cost vector, the difference would be 9 because one direction we have 0, the other direction we have 9. So this particular binary classifier is very similar to the one used in CSOVO, one of them. Okay, just comparing class 1 versus class 2. Similarly, for comparing class 3 versus class 4, we can form one binary classifier. Which one is more preferred? For this particular example, the smaller c is C3, right? Okay, so the left one is more preferred, and the difference, okay, is 3. The cost difference is 3. So we can train those two binary classifiers. If we train those two binary classifiers, then we know for each example, okay, which direction each of the classifier would take. So we can then take this to an upper level to train this particular classifier, saying, okay, should I walk left or should I walk right? Okay, which one would lead me to the lowest cost direction? So this filter tree approach trains from bottom up, and in each bottom up level, it tries to form classifiers to guide the higher level of decision. If the lower level classifier makes some mistakes, okay, then the higher classifier would also know and prevent that mistake. For example, in this particular case, obviously C1 is lower than C2. But if the classifier makes a mistake and walks to the second leaf instead, then the top level classifier should know to not go to the left subtree, because if it goes to the left subtree, then it would pay a cost of 9. So for the top classifier, knowing that the underlying classifier may make mistakes, it would choose to go to the right, okay? Hopefully suffering from a smaller cost of 5. So this is the filter tree approach, okay? Maybe it's not super easy to explain it in real time, but at least I want you to get the idea that it tries to form simpler classifiers in the lower level. And if those classifiers make mistakes, the upper classifiers know about those mistakes and will tune the decision based on those mistakes. That's the filter tree approach. And it's efficient because it only requires order k in training. Okay, so basically in training, the number of classifiers in this binary tree is just order k. And in prediction, we can do it in a top-down manner. It costs only log k. And there's a strong theoretical guarantee saying that for all those binary classifiers, if they have a small regret, okay, which is one way to measure how it performs relative to the best binary classifier that you can get, then we can get a small regret cost-sensitive classifier as well. And how about counts? Okay, this filter tree approach puts all the labels, okay, in some particular order. Okay, in the leaf, and comparing 2 of them in each iteration only. So this is much like the Olympics game, right? Okay, your opponent is kind of important. Okay, it affects you could get the champion or not. So because the role of the labels are not symmetric, there's a non-trivial structural decision to decide which label gets compared with which ones towards the final decision. And basically with this approach, the top level classifiers, okay, are harder. Okay, because it needs to be aware of the lower level mistakes and make adjustments or corrections, creating harder binary classification data sets, actually. And those are the disadvantages that prevents filter tree from better practical performance. In the literature, there are other reductions, other transforms from multi-class cost-sensitive classification to binary classification. And let's illustrate in a very high level what they do. There's the filter tree approach saying, okay, in each classifier, it's basically doing some sort of group comparison, okay, in terms of the achievable costs, okay, the costs from the bottom level subtrees. Now, there's another way of using the tree decomposition called divide and conquer tree, or simply tree. And it's ask the same question, but with the ideal cost. Ideal cost means the best cost within the subtree. Okay, so we can also use this to form a tree-based reduction, but as the literature shows, this comes without the regret bound, while filter tree comes with the regret bound. So filter tree is generally considered a theoretically stronger guarantee algorithm. And there are other approaches with regret bound. Okay, one particular approach is called sensitive error correcting code. It's roughly asks whether some of the costs, okay, some to be greater than a theta. Okay, so basically, it's using multiple kind of these comparisons to determine which costs, which class is of the lowest cost. To make the prediction. Okay, so this is called error correcting code kind of approach. We won't go into the details of this approach, but just trying to help you understand that there are these different approaches trying to convert the cost information to binary labels in some different ways, okay, towards understanding which cost component is of the lowest. Now, in terms of training time, most of them are linear. Okay, those tree reductions, they are linear because the number of nodes that we have are linear. And in the error correcting code approach, it's proved that we need roughly a linear number of codes to get good performance. Okay, so in terms of training time, mostly linear to the number of classes. Let's compare their performance with cost-sensitive 1 versus 1. Okay, so all of them are reductions to binary classification, and we have 4 different approaches here. The blue one, CSOVO, the light blue one, filter tree, and the green one, tree, and the yellow one, sensitive error correcting code. Again, the vertical axis shows the average cost, so the lower the better. We see that generally cost-sensitive 1 versus 1 is better, the dark blue one, showing that stability matters. Okay, cost-sensitive 1 versus 1 really enjoys better stability. Filter tree is okay. Tree is not really better than filter tree. So generally, it's recommended to use filter tree if prediction time is a concern, while sensitive error correcting code is not a very good approach, actually, because it creates very noisy binary classification data sets. Okay, so the readout from this figure is that CSOVO often is the best, it's the more stable choice. Filter tree is okay, especially if you want to focus on faster prediction time, but if you have more time, maybe CSOVO would do well. Okay, that's cost-sensitive classification by weighted binary classification. Let's see if we have any questions here. Okay, why don't we just add a weight term in the loss function? Each weight represents the cost of each class. Then we can use any multi-class classification algorithm to solve cost-sensitive classification problem without complex settings. Thank you. Okay, one reason is that we cannot just add one weight in the loss function. Actually, as you can see in our formulation, each example is connected to k-1 cost values in the multi-class case. Okay, so if you want to modify your loss function, it is non-trivial how you would plug in those k-1 values, okay, as proper weights in your loss function. You can do that, but it requires some thinking. Okay, it's not that trivial. So that's what we mean by cost-sensitive classification being more sophisticated than weighted classification. For weighted classification, each example carry one weight. You modify the loss function using that weight, you get your weighted classifier. But for cost-sensitive, at least for multi-class cost-sensitive, each example k-1 different values, and it is very hard to have a principled way of plugging in those k-1 values properly into your loss function. In slide 37, why do we only have 2 classifiers and not 4? Okay, let's see slide 37. Okay, in 37, they form a tree-based approach. In a tree-based approach, basically it just says, okay, I put the classes in some order, and here I'm using metro order 1, 2, 3, 4, and I'm only allowing the class neighbors of the neighboring leaves to make the comparison. So I'm making one single tree based on this structure. Or you can say this structure is predetermined. Filter tree tells us if you give me this structure, how do we train the classifier to get the best performance? Okay, so if you want other comparisons, for example, if you want comparison between 1, 3, or if you want comparison between 1, 4, then you need a different structured tree for that. And for this particular tree, in the lowest level comparison, we're only doing 1, 2, and 3, 4, much like the elimination game that you see in Olympics. Okay, but how do the ancestor classifiers know the subtree classifiers are wrong? Just what will happen if both child classifiers are wrong? Just pick the smaller one, or it will terminate the process. Okay, short answer, we train bottom up. So in the bottom up training, when the ancestor level, the top level classifiers are being trained, the bottom level classifiers have been trained. when the classifiers have been trained, you can use that classifiers to predict on the training example. You have the training example, you use them to predict. When you use them to predict, you know which direction those classifiers would choose. Yes, some of the classifiers are wrong. Maybe all of the classifiers are wrong. But then the top classifiers know to pick the least harm choice, the most harmless choice. Okay, so the top classifier can make the best performance. Okay, so that's how the filter tree work. Okay, start from the bottom, knowing the limitation of the bottom classifiers by rerunning those classifiers on the training examples, and then use those decisions from the bottom classifiers to determine the best choice from the top classifiers. Okay, thank you for the questions. And now we're done with multi-class with binary classification. Let's now connect multi-class classification, co-sensitive multi-class, to regression. And you see that this is actually one fascinating direction within co-sensitive multi-class classification. It's connecting it with many of the tools that we're familiar with in other setups. So regression, let's see. Our goal is to a classifier that pays a small cost. One way to think about this is if we know where what the cost would be, then we can make an optimal decision, right? Similar to what we did in a base optimal case. In the base optimal case, we assume we know the probability estimate, then we make the optimal decision. Now, if we know the cost vector, yes, I know it's a super big assumption to know the cost vector, but let's say we know. Then the optimal choice is obvious. You just pick the smallest one. What we don't know. In the Bayesian optimal case, when we don't know, we estimate. Now we can estimate as well. How do we estimate? We can use regression to estimate each cost component. And that's the approach that we're going to talk about here. I'm going to use these functions RK to estimate each cost component from the examples. And then if we can get a good estimate, we can get a good classifier. It's that simple. Regression as the estimate, okay, and get the estimate and apply the optimal decision making if you know the cost vector. So what do we do? If we have all those inputs and the cost vectors on hand, what we can do is for the first component of the cost vectors, we form a regression problem. And let me call this R1 from X to the first cost component. Okay, you all know how to do it. You can do linear regression, you can do neural network regression, you can do whatever regression of your favorites. Second one, regressor 2. And case 1, regressor case. So you get each problem, you reform each problem, get a regressor, get a regression estimate, and with the hope that this regression estimate will be close to the cost vector for future examples. Much like what we do in regression, right? Regression means you do an estimate with the hope on future test examples, you can estimate the value, you can predict the value correctly. Here, the values being predicted are the cost values. So this is the reduction to regression framework. Okay. Much simpler than all of the algorithms that you see previously. From the cost-sensitive example, we form regression examples and throw those examples into a regression algorithm, gets the regressors, and then when we do the decoding, we just pick the minimum regression value for each example and use that as our classification results. This is systematic, super easy to implement, I bet. Most of you can implement it in scikit-learn in an hour or two or something like that. Okay, and this simple framework carries a strong theoretical guarantee. What we proved is that if we look at the absolute loss, okay, absolute error between the regression output and the actual cost, then there's this bound. Okay, this bound tells us the costs that we're interested in on the left-hand side is upper bounded by the sum of absolute regression errors. So if our regressor is close to the actual cost, then the cost we're paying for our classifiers is small. That means accurate estimators can be turned into low-cost classifiers. And not just absolute error, we can derive something similar for the square error as well, which can be applied to, for example, linear regression that you're familiar with. Okay, similar results. Okay, accurate regression give us very accurate cost-sensitive classification. Okay, and this result is actually not too hard to prove. Okay, so I'm trying to give you a pictorial proof within this slide. Without loss of generality, let's assume that we have a cost vector for some example like this. The optimal class is the first one, and then we have class 2, class 3, class 4, and so on. This is just for illustration. Okay, you can think that we can always shuffle the classes for each example to get this cost vector sorted, but making things sorted actually makes this pictorial proof much easier. And let's say we make a misprediction to 2. The best class is 1. We make a misprediction to 2. That must mean our R2 tells us a smaller value, right? Best prediction, 1. Okay, that means okay, R1 should be the smallest, but somehow we predict 2. It must mean R2 says, I have a smaller cost, I have a small cost, pick me, pick me. Okay, then what should happen? We have C1 here, we have C2 here. Of course, we have other values, but they're not important at the current point. Let's look at R1 and R2. R2 must be smaller than R1. Okay, R2 must be smaller than R1, so a misprediction happened. And we have R1 here, we have R2 here. Let's look at the 2 errors. We have delta 1, the error between R1 and C1. Delta 2, the error between R2 and C2. To make R2 so small that it's smaller than R1, either R1 or R2 must deviate from C1 and C2 a lot, such that delta 1 and delta 2 are big enough to cause this error. Actually, there are several different cases, but I'm illustrating the most important case here, telling us this distance, C2 minus C1, where C1 is 0. So this is actually the C2 we need to pay is smaller than delta 1 plus delta 2, where this delta 1 is how much R1 deviates from C1, and delta 2 is how much R2 deviates from C2. To make R2 so small, the deviation must be big enough such that this delta 1 and delta 2 becomes larger than C2. And the bound that I showed you is actually just a looser case of this particular proof. Okay, so the most critical delta are those 2 cases, but generally to have a simpler bound for you to see, and just using a looser presentation here. Okay, so this is a pictorial proof of what we did with this reduction. And actually, this proof is not totally complete. I'm showing you some refinements. What are the refinements? I just showed you the case where we have delta 1 positive and delta 2 positive or non-negative. And this easily tells us that C2 is less than the sum of 2. But actually, there are other cases. For example, R1 is so wrong. Okay, and it's actually worse than C1. But R2 is even worse. That's why we make the misprediction. Then we see delta 2 itself can explain the cost difference, can upper bound the cost difference without needing to rely on R1, rely on delta 1. Or there are other cases, okay, where we actually, I'm not showing the case here, but this particular case says if R1 is super big, okay, much bigger than what we have, but even a small delta 2 can explain the whole situation. And that's another case. But anyway, I'm not showing the full detail here. But what we can refine is that by having a polar definition between delta 1 and delta 2, you see that their polar sides are different. This one is R1 minus C1. This one is C2 minus R2. Okay, and with this polar representation, we actually have C2 upper bounded by a tighter term. That's the taking the max between delta and 0. If delta is smaller, we don't need to count that. If delta is bigger, we count that in the error term. And this is basically what we did in one of our earlier works. Okay, so basically defining the error term that we're actually interested in a one-sided manner. One-sided meaning if it's negative, we don't care. If it's positive, then we charge for some penalty. And two different cases represent the classes with the minimum cost or without the minimum cost. The intuition behind this is that if it's the minimum cost, we want the regression to output actually even smaller values. Okay, we want the regression to underestimate the cost values because underestimating the cost values would just give us a stronger chance to predict correctly. While for classes that are not of the minimum cost, we run the regression algorithm to predict as big as possible. We don't care about accurate. Actually, we want it to predict as big as possible so our classifier won't make the mistake. And both wishes are just encoded in the intent of delta k minus less than or equal to 0, which can be expressed with this special error term. And we can use this to derive a tighter loss bound. This tighter loss bound allows us to design what we call one-sided regression algorithm. So in addition to regression label, we add another label telling the machine which side we prefer. The lower the better, or the higher the better. And then we take one-sided regression algorithm to get the estimators and get better performance. So you can view this one-sided regression version as an improved version of the original regression algorithm. Now, the only thing that we need is to just say, okay, do we have a good one-sided regression algorithm? What we did, actually, this is the very first work that we did, an ICML work, when I came back to Taiwan, is to use SVM to decide the one-sided regression algorithm. I'll skip the details here, but generally, we use an SVM-like formulation to write down a projective programming algorithm to solve this one-sided regression problem. And this one-sided regression problem is actually much like the usual standard support vector regression problem, but standard support vector regression, you have two sides, two kind of variables recording whether you have violations on the top or on the bottom. While one-sided regression, we only have variables for one side. And this gives us an algorithm that's called one-sided regression, SVM, for cost-sensitive classification. And at that time, we studied the connection between one-sided regression and the traditional one versus all algorithm, which can be viewed as a costless version, a regular classification version, while this one-sided regression is a cost-sensitive version. 10 data sets and average test cost, so the lower the better. We see that one-sided regression, which is in blue, is usually better than one versus all. And this tells us that considering the cost information helps. Again, I mean, I assume that you are a little bit tired of this message, but for each new algorithm, we need to highlight that again. And also, it is better, it is competitive. This one-sided regression algorithm is competitive to another algorithm called weighted all pair, which is similar to CSOVL as we discussed. But one-sided regression requires less time in terms of training and prediction, and therefore should be a preferred choice for SVMs. That was the result that we got back in 2010. And a few years ago, we extended this SVM idea to deep learning. And in deep learning, we don't have projective programming, but we use an approximation of this one-sided error to basically get a more smooth loss term. And this smooth loss term, as you can see, have all those log exponential there, similar to the usual cross-entropy loss function that you would use in neural networks. And this particular algorithm just applies one-sided regression with deep neural network, and to get a smoother formulation to solve. Okay, so that's the deep learning version of the one-sided regression algorithm. Now, what's the problem with this deep learning version? We find that this cost vector actually should affect both classification and feature extraction in deep learning. Okay, but if we directly just plug in the loss function, then the deep learning model may have some issue propagating the cost information within the network. And therefore, the feature extraction performance is not too well. How did we solve it? In our very first work, we proposed pre-training. Okay, so basically, we designed a pre-training approach, okay, based on one-sided regression, so we can push the cost information to earlier layers of the network. That's the work we published in 2016. And another idea is to add nodes to each layer of deep learning. Okay, add auxiliary nodes to each layer, and those nodes are used for predicting the cost. And with those layers, then what we can basically do is to use those to guide the feature extraction process. And this was published last year in a conference. It applies to any deep learning model. And this kind of model is, to our knowledge, the first successful deep learning model that introduces the idea of cost-sensitive learning. And what we can do here is to compare their performance. Okay, the comparison here is the blue bar, which is the preliminary version using one-sided regression, and CSDNN, which further improves the model by introducing cost-sensitive pre-training into the model. The lower the better, and in terms of average test cost, and we see that the red bar, which is CSDNN, that has cost-sensitive feature extraction, actually achieves better performance. This shows that considering pre-training properly is helpful. Actually, it's very important in the deep learning age to put cost into feature extraction as well, not just the final loss function, but into the pre-training process. And also, we can compare ABOD. Remember our old friend? Using Bayes estimate. Okay, we can use deep neural network to do probability estimate. We often do that nowadays, and couple it with deep learning, and couple it with cost-sensitive classification by doing cost-sensitive prediction. And we also see that CSDNN, which considers cost-sensitive feature extraction, actually also does better. This hints the difficulty of probability estimate. Actually, without the cost-sensitive feature extraction, it cannot do that well. Okay, so that finishes all I want to talk about in terms of cost-sensitive multi-class classification, ranging from very beginning of earlier works in terms of Bayesian estimate, and along the way to weighted binary classification and regression. Let's see if we have any questions here. Okay, there's one question asking why it's R4 but not R6. And let me go back to that page to help you trace what's happening. I assume it's in the filter tree part. Okay. Now, in the filter tree part, I assume that the student is asking about the top node, where the decision is R4. Why is it R4? because if we follow the tree and go left, and we see that the decision of this classifier, as hinted here, is 9. So we would go to the leaf of 9. Or if we go to the right, okay, then we would follow this classifier and go to 5. And this particular 4 is the difference between 9 and 5. Okay, so basically the cost difference between these two choices. So the difference being calculated here is not the difference between 9 and 3, which is 6. It is the difference between 9 and 5, which is 4. Okay, what if we do not know about anything about labels? Is the cost matrix still promising? Okay, let me reformulate this question in another way. So cost matrix can serve as additional information you have about the labels. Okay, you have the labels, that's the usual traditional regular classification, and now cost is additional information. Okay, your application is telling you which errors are less favorable, which errors are more preferable, and so on. So we're talking about how to use this additional information property. If we don't have label information, okay, that's the area of weekly or semi-supervised or unsupervised learning, okay, where if we don't have other information, actually it's not label or cost information, we need to find help in other kinds of information to guide the learning process. But then it may not be the cost, okay, it may not, it may be other information that we want to use. Okay, so done with multi-class. Let's go into multi-label classification. Okay, as usual, let's start with motivation. We had the classification problem, and now I'm motivating a classification problem by a fruits recognition problem, just like the other classification problem that we have seen. And now we're introducing a more complicated problem. Okay, we're predicting which fruits are in the picture, not which fruit. And so you see there can be multiple fruits in the picture. We're classifying the input to multiple or maybe no categories. And this is called multi-label classification. And there's one very simple approach for multi-label classification. Okay, if we think in a multi-class classification problem with 4 classes, we have 4 possible outcomes. Multi-label classification can be just viewed as a classification problem with 16 possible outcomes, 1 for each power set of the class. Okay, one for each superclass within the power set. So there are 16 possibilities. And to basically separate between this multi-label classification with the multi-class classification that we talked about, we use L to illustrate the number of classes here. And this label power set approach can be viewed as a reduction to multi-class classification. And it's difficult for a large L, as you can imagine, because there are 2 to the L extended classes or superclasses. And each class may not have enough number of examples. So this label power set approach is feasible only for a small number of labels. Let's see another multi-label classification problem, and let me shamelessly use the books that I co-authored as an example. Okay, and the book is selling on Amazon, and on Amazon or as in any e-commerce platform, you'll see that basically books or other things are tagged, right, to help the users search what they want. Okay, so this particular book may have some tags associated with it. For example, it's a machine learning book, it's a data mining book, it's a textbook, but arguably it's not a compiler book, it's not a children's book, and so on. So it's associated with some of the tags and not associated with the other tags. This is another multi-label classification problem. We're tagging the inputs to multiple categories. And for this, we can see one very simple way of solving the multi-label classification problem. Basically, we know how to solve yes-no questions. Yes-no questions are just binary classification. And for multi-label, we can view each tag as a binary classification problem. Okay, so we can predict whether this book is for machine learning or not, whether this book is for chemistry or not, or whether this book is a textbook or not. Okay, so if we have L different classes, then we have L different yes/no questions. And this is called the binary relevance approach for multi-label classification. We're doing a reduction to multiple isolated binary classification problems. But people usually challenge on whether this kind of reduction is good, because isolation essentially hides the relations, okay, between different classes. For example, in this particular case, you see that machine learning and data mining are correlated. Machine learning may be a subset of AI, and textbook and children's book are disjoint, and so on. Okay, so there are relations among those labels, among those classes, but those are not modeled by this binary relevance approach. And each binary relevance problem can be unbalanced, because generally, as in the tagging problems that you can imagine, there are few yes cases and many no cases. This approach is simple and has known disadvantages, but I want to give you some bigger picture that it is actually a strong benchmark. Okay, in many of the multi-label classification works, this is one of the first benchmark you need to compare to ensure that you are making some genuine improvements. Okay, so multi-label classification, this is the problem we're going to deal with in this part of the lecture. And our goal is to get a multi-label classifier that closely predicts the label set associated with the examples, with the hope that we're exploiting the hidden relations or combinations between the labels. And in the past few years, it's actually a very hot and important research problem with many real-world applications. Actually, even now, several of my lab members are working on related problems. Before we go further, I'm going to introduce you the one coding view of this multi-label classification problem. Basically, what we're trying to do is to convert the label sets, okay, which is a discrete structure that we're trying to predict, to binary code, okay, which is again a discrete structure, but easier to manipulate for many computer-based algorithms. And this binary code is simple. Okay, for each label set, we can take a binary relevance-like approach to list the yes/no answers and use a binary code to encode those. So for example, if there's only one orange, then the corresponding binary code can be 0, 1, 0. While if there's an apple and an orange, then the corresponding binary code would be 1, 1, 0. Okay, so it's just an equivalence transform between the subset to a length L binary code. And with this, we can view the label parset approach as a reduction process that encodes the binary vectors to multi-class labels, and then learn with any multi-class classifier while predicting with a binary representation. So basically transforming each binary code to a single number for the multi-class classification to make prediction. And naturally, now that we talk about multi-class classification, very natural evaluation of performance is called 0-1 error, or in the case of multi-label classification, it's usually called subset 0-1 error. You just compare whether the subsets are the same, much like the regular classification error that we see in multi-class classification. Now, this is a strict measure for multi-label classification, as you can imagine, because it requires every bit, okay, every element in the subset to be predicted correctly. While in the binary relevance approach, then we can also use reduction to illustrate that. Basically, it converts each example to binary examples and use binary classification to learn from those examples and then just decode from the binary predictions. Now, given that each binary classifier is predicting separately, we may wish to evaluate each binary prediction, each yes-no result separately as well. And this leads us to the usual Hamming error, which computes the set difference, okay, between two sets and average it, okay, to get the performance. So every bit of error would contribute to 1/L of the Hamming error. And this is a simple measure for multi-label classification that many people uses. Now I'm introducing you two error measures, subset 01 and Hamming. And actually, there are different error measures. And also you see that different approaches, label power set, binary relevance, they kind of optimize different kinds of errors. And different kind of errors encode different kind of dependence, actually. For example, in this work in 2012, it's argued that when there's a strong dependence, okay, between labels, then joint optimization is really needed and should subset 01 error should be used. While if there's no conditional dependence, okay, there's no strong dependence between different labels, then we can use the Hamming error. Okay, so different error measures, okay, are needed in some way based on different assumptions to the problem. And different applications may need different measures. For example, for information retrieval, maybe you don't want 01, you don't want Hamming, you want F1 score in some way because it measures precision and recall better for this application. While for tag recommendation, you want the more relevant tags to be in the front while don't care that much about the irrelevant one. So you may want to use the ranking error. And there are other errors, other measures that you may want to use for multi-label classification. That's when we sort of formulating the cost-sensitive multi-label classification problem, okay, which wants to design one approach for any measure, much like what we did for cost-sensitive multi-class. One approach for any measure, one approach for any cost matrix. And that's the problem we'll focus on here. And we'll consider multi-label classification inputs, but now with a cost function. I'm not using a matrix because for a matrix, this would just look super big, okay? And when using a function, a more regular patterned function, in some way we can represent the intent more succinctly. Okay, so we have a function here, and this function has the cost information that we want. And again, we want to get a classifier that pays a small cost with respect to this function in the future. And this is called an instance-based cost-sensitive multi-label. Each instance is evaluated separately. There are more sophisticated cost-sensitive setup, but I'm not going to talk about this in this lecture. If you're interested, you can check one early work of ours in 2018 for this result. But now we're dealing with the simple one. Each instance, we throw into the cost function to get the evaluation. We sum all the evaluations, or we average all the evaluations to get the results. Okay, and we'll focus on this setup first. For simplicity, actually, it's not that simple. You will see even with this setup, it's non-trivial to get a good solution. Okay. I don't see any more questions in the forum, in the chat. So maybe people are getting exhausted and so on. And by the way, we still have 3 different topics, 3 different techniques that I want to cover, but we are at 5 p.m. here in Taiwan, so I'm not absolutely sure how much time we have. In the worst case, I'll cover the first one or first 2, and then jump to the application story, because actually it's more interesting for everyone. While if you're interested in other parts of the material, you can find the tutorial that I gave at KDD 2019, which should be freely online, actually. Okay, let's go to cost-sensitive multi-label. Can we do Bayesian optimal decision? certainly. But now it's more complicated. You have a cost function, okay, that's evaluated on 2 to the L terms. So that means when you want to do the base optimal decision, even with an estimate of Q in there, you need to do summation over 2 to the L. You need to do minimization over 2 to the L. Okay, both of which are time consuming. And of course, when you have 2 to the L outputs, it's very hard to do probability estimation as well. So idea is simple. You do base optimal like what we did for multi-class, but implementation is hard. You will definitely suffer probability estimation, cost calculation, and inference. Okay, those issues. Now, how do we do? Okay, let's first conquer the probability estimation problem. One way to do that is to assume some independence or some sort of decomposable structure between the estimate that you want to get and get it separately. So this is one particular decomposition that people have considered. We estimate several binary probability estimates. The first one being Q1, estimating what the first label is. The second one being Q2, estimating what the second label is, conditioned on the first label. Okay, so conditioned on the example given and conditioned on the first label. And the third one, okay, predicting what the third label is, conditioned on the inputs, the first label and the second label. Okay, so this decomposition forms a chain of estimation, and each estimation just need a binary probability estimate that can be done with, for example, logistic regression. And if each probability estimate is accurate, then you can use independence for this multiplication to get an accurate estimator for the joint probability distribution. And this is called probabilistic classifier chain. Okay, it's called a classifier chain because structure-wise, it seems to be connecting each different binary classifier together. Okay, the prediction from the previous classifier, the first classifier would affect the second one and the third one and so on. Okay, so it's a decomposition to conquer the difficulty in probability estimation. Now, how do we conquer the problem of evaluation? Well, to conquer that, okay, we need to avoid estimating 2 to the L different y, okay, 2 to the L different cases. And the conjecture or the assumption is really that, okay, there are only a few cases where P is big. In other cases, okay, because the space is so big, the probability is small. So we can try to draw some typical ones, okay, by sampling. Okay, for example, if you have a joint distribution Q formed by those marginal distributions that you estimated, then you can do sampling there, okay, and sampling would give you some higher probable combinations while you treat the other ones as zero. Or you can keep, okay, the most probable ones, okay, by doing some sort of search, okay, within the space, usually called a bin search, okay, keeping most probable predictions. And those are ways that people use to conquer the difficulty. So basically by keeping the most representative combinations. Now you have a small representative Y, you can use that to evaluate the cost. Then how do you conquer the difficulty of having exponentially many targets for prediction? How do we do? Well, some of the C allows efficient inference. For example, if your error, okay, is just subset 0, 1, okay, then you just want to predict the one with the maximum Q. All those representative one, okay, gets the maximum Q. That's the optimal prediction. We can analytically solve that. Hamming error, we can analytically solve that. Okay, so basically trying to use majority vote, okay, to get the optimal prediction. So sum of the C, efficient inference, and we can solve that very efficiently. But that's only for some specific C. If it's general C, then it's difficult. Okay, so that's what people generally do for this LBD direction. We do probability estimate with decomposition. We sparsify the estimation with representative one, and we derive efficient inference rules. But if there's no efficient inference rules, sorry, this approach will still have difficulty in the very last step. Now, a concrete approach to for this idea is the probabilistic classifier chain. Okay, so in training, each Q is learned with inputs and outputs up to the L-1 level. And in inference, there's representative by bin search, and then trying for subset 0-1 error. That's the argmax inference. Now, this is one counts. Okay, there's non-trivial structural decision, much like what we did for filter tree. It's non-trivial decision, which label goes first, which label goes later. And therefore, it's often randomized in some way and using ensemble to improve the performance. And it can be time-consuming during inference, okay, depending on how many representatives that you have. And for a special case of B equal to 1, it corresponds to a very traditional approach in multi-label learning called classifier chain. Now, for F1 score, people have actually derived efficient inference rules, okay, after simply estimating some of the necessary statistics, and there's algorithm with order LQ computation that can give you the best prediction for F1 score. So not just subset 0-1, not just Hamming laws, but for F1 score, there's inference, efficient inference as well. Okay, but it still needs to rely on, for example, sampling and training for probability estimation. So mini summary, subset 0-1, mode, okay, the maximum case. Hamming, okay, stressful for the marginal one. Ranking, you can sort Q and F1. There are necessary statistics that you can compute from Q. But there are other cases, okay, such as this particular one called accuracy, and also a multi-objective combination there that are without efficient inference rules, in which it's hard to use the PCC family. So for a PCC, it's cost sensitive in principle, but in practice, it can be only used in those green cases where efficient inference rules have been derived, while it's hard to extend PCC to other cases when we don't have efficient inference rules. Now let's look at some results empirically. There's PCC Hamming, there's PCC F1. PCC Hamming is in blue, PCC F1 is in red. And left-hand side, Hamming error, right-hand side, F1 score. Hamming error, the lower, the better. And you see, the blue one is often better. F1 score, the higher, the better. And you see, the red one is better. So this shows us that considering the cost properly is still very important for multi-label classification. Feeding the right cost actually gives you better performance with respect to the cost that you're interested in. Okay, so that's the algorithms from a Bayesian perspective. Let's see if there are questions from the audience. If we estimate the joint distribution of labels, would it be helpful for multi-label classification? And the short answer is yes. Okay, and my point is actually the estimation itself is hard. Okay, you see that PCC requires estimating using the decomposition. Of course, you can form with other decompositions or joint estimation or whatever to do the estimation, but the estimation itself is not that simple. Usually you are facing, because you're in an output space of 2 to the L possible outputs, you are facing combinatorial explosion there, or for many of the cases, you just don't have enough example to estimate the probability well. Okay? And that's, again, echoes the disadvantage of Bayesian-like approaches. They rely on good estimates, but good probability estimates are hard to get. Okay, now let's go to weighted binary classification. And this is one of my favorite parts, okay? We talked about how we can just connect multi-label to multi-class with the regular cost. And this gives us the label parset approach for multi-label classification. Now, if we have a cost, what happens? Well, you can think it's very simple. CSML, we feed the cost function to multi-class classification, then we get a problem cost-sensitive multi-class classification. So it's as simple as that. Okay, the cost function we are interested in multi-label classification can go through the same label parset construction to give us immediately a problem of cost-sensitive multi-class classification. Disadvantages, it's super complex, right? You have 2 to the L super classes. Okay, for example, if you are combining it with Bayesian approach like what we did, then you need 2 to the L estimates. And we just see you basically need more decomposition, spatial inference, and candidate selection, other approaches to conquer that. Can we couple this with CSOVO? Yes, we can. Okay, but CSOVO, remember you have 2 to the L, choose 2 classifiers. Too many to for any reasonable computation. So basically, you need sampling, you need some efficient decoding to do that. That's in one of my students' work, and I'm not going to talk about this today, but I'm going to talk about cost-sensitive label parset with filter tree, because it gives us a very interesting algorithm in the end. Remember, filter tree is tree-based decomposition. Okay, and this tree-based decomposition actually allows us to have 2 to the L leaves of the tree, but the height of the tree can be kept basically at a shorter level. So let's see what this approach is about. Now, let's see. If we combine CSLP with filter tree, this is basically what we get. Remember, in the filter tree, we have different classes, 0, 1, 2, 3, and we have different intermediate classifiers and then the top classifier. Now, if we do the label parset encoding with the binary bits, okay, so this is 0, 0, 0, 1, 1, 0, 1, sorry, this should be 1, 1, okay, my typo here, this should be 1, 1. And then we see that each classifier in the middle actually compares 1 bit. Okay, so this classifier between superclass 0 and superclass 1 is comparing the second bit. This classifier between superclass 2 and superclass 3 is again comparing the second bit. Of course, this is 1, okay, as mentioned. So this layer, this blue layer, comparing the second bit. After comparing the second bit, this top layer compares the first bit. So by encoding our binary vectors, or connecting our binary vectors to the classes with what we call a binary number encoding here, each classifier in the filter tree has a special physical meaning, just predicting one of the labels, like the classifiers in classifier tree or binary relevance. So if we follow the filter tree approach, how many predictions do we need? Well, we follow the tree from the top to the bottom. How many levels do we have? Predict first bit, predict second bit. So we need 2 predictions, log 2 to the L, which is just L. So this is like binary relevance. You go through each prediction, you get the result with the help of the filter tree structure. But still, there's 2-to-the training complexity, because if you check the number of internal nodes, first internal node, second, third, we have 3 internal nodes, okay, for these 4 superclasses. So now what we need to do is to conquer the training difficulty of these internal nodes. What can we do? Let's look at what these internal nodes are doing. This root node is predicting whether we should predict the first bit as 0 or as 1. This is just like binary relevance in the first level. First prediction, nothing. But in the second classifier, things are a little bit interesting, because here we're saying condition on we are on the left subtree, what should we do? Here we're saying condition on we are on the right subtree, what should we do? So this condition can be embedded as another input to this classifier G2 that can be shared by this level. So originally we have 2 classifiers in this level, but I'm sharing those 2 with one classifier I call G2, but distinguish them by another input that I send to those classifiers. So second layer classifier can be shared, okay, condition on what we have in the first level. So these 2-to-the-L-1 internal nodes becomes L classifiers, 1 for each level. So this is the idea of classifier sharing. And this gives us a structure very much like PCC. PCC, in each level, we have probability estimates and added by predictions from the previous level. In this CSLP plus filter tree approach, in each level, we have a classifier. But this classifier is parameterized by predictions from the previous level. So this is just CSLP plus filter tree. But now, how do we train those classifiers? If we rigorously follow the filter tree, then we still need to split all our examples to training different levels of classifiers, right? And how many cases will we encounter? We would encounter 1 case for each internal node. Still 2-to-the-L-1. That's too much, right? Okay, so what do we do? Another idea is that basically we only update the classifiers that are more relevant. And for classifiers that are less relevant, we just don't generate those. This idea is much like what we did for the Bayesian case. Okay, the Bayesian case, many of the probability estimates are close to 0, so we dropped it. We picked the more promising one as candidates. Now we pick the more promising one that we will encounter in the tree path to train the classifiers. And this is called the condensed filter tree algorithm. So label parsets, filter tree, and keeping only those examples near the prediction path. Now, this is the final algorithm. You see it combines several ideas, starting from the original reduction, then we do proper ordering so we can see the structural similarity to classifier train. We do the classifier sharing, and then we do example sampling near the prediction path. How does the algorithm perform? Okay, there are 3 algorithms we compare here. Classifier train, which is without cost information. PCC, which is the green one with the cost information. And condensed filter tree, that's the brown one with the cost information. We see that for the F1 score, where the higher the better, basically CFT is competitive to PCC kind of approaches, okay? Very similar performance to PCC with F1. And remember, in this case, PCC with F1 has efficient inference rules that we can use. Okay, so this actually justifies the CFT to be competitive. And there's one slide that I didn't show here, showing that for inference, for cases where PCC does not have efficient inference rules, then condensed filter tree can do better. Okay, so this actually tells us that CFT can do more general than PCC in terms of digesting more general cost information. Okay, I bet everyone is exhausted, so please allow me to just skip this CSML by regression part. I'm sorry about that. But if you're interested, feel free to drop me a line or check our previous work or my previous tutorial for this part. This part also has something interesting, okay, but we may not have time to cover that. And I want to directly jump to a discussion. Okay, now that we hear cost-sensitive multi-classification, we hear their extensions to cost-sensitive multi-label. Now let's go back to cost-sensitive multi-class classification. I started doing related research on cost-sensitive multi-class classification, actually not 10 years ago, okay, almost 15 years ago. Okay, and at that time, this was the picture when we started. We have well-studied regular binary classification. We had well-studied regular multi-class classification. We have some known result for binary cost-sensitive. And we zoomed into the multi-class case, along with other very great researchers along that age. And we have done some interesting works along the line, like the SVM that you saw with one-sided regression, the one versus one algorithm, which is a very robust choice, and extending the thoughts to deep learning, okay, which was kind of our latest work along the line. And when doing this work, I kept asking myself, why are people not using all those cool works for their applications? And that's the story I want to share with you in this very last part. Okay, are we making machine learning or cost-sensitive classification more realistic? Okay, are we really close to that? And what are my lessons learned along the way? Okay, so one very first question. Many of you asked those questions during our lecture as well. Where does the cost come from? Where do you get the cost? Okay, and actually not just you. Many of the reviewers from our past works gave us this question. We keep emphasizing, you can give us any cost and we can do well. And they say, no, I don't believe you. Where do you get your cost? Okay, fine. So at one point, I say, let's see if we can have some opportunities to get the cost and justify whether we can do well. And this is one particular opportunity that we got 10 years ago. It's automatic classification from the spectrum. Okay, this is a particular way of getting the spectrum to bacteria. Okay, so basically, they will have some way of scanning the bacteria to get the corresponding spectrum, and each spectrum should describe some bacterium that we are interested in. And for this question, are all misprediction costs equal? For some of you with more biological background, okay, you may actually know some about this. Okay, so for bacteria, there are some bacteria called gram-positive, and there are some bacteria called gram-negative. And basically, they require different treatments. Okay, so if you misuse the treatment for gram-positive gram-positive to the gram-negative infections, then there can be serious results. So gram-positive as gram-positive, that's an error, but small cost. Gram-positive as gram-negative, it's an error with big costs. It can harm patients' life. So knowing this domain knowledge, we ask two doctors to give us their cost matrix. This is a 10 by 10 cost matrix. Two doctors, so each of them fill 100 entries or 90 entries. Okay, if we exclude the diagonal part, and we average the two cost matrices. So now we have the cost matrix. Okay, for basically most of the cases in the cost matrix, I don't know what bacterium it means. I only know the second one, which is E. coli. Okay, some of you may know about this. For the Mandarin speaking, that's 大肠杆菌. But anyway, we are the algorithm designer. We have those spectrums from our collaborator. We have the cost metrics from our collaborator. Let's see if cost-sensitive classification is really useful. So not just those UCI simulated data sets. This is for real. This is really getting the data from domain experts and trying to improve the performance there. Okay, can we do better? Now, these are two cases from our earlier paper, and we see that there's OVO, there's CSOVO, the orange one, CSOVO, and the red one, OVO. Okay, so this is the vertical axis is the test cost, so the lower the better. Now you see, while the error bar is not too significant yet, partially because at the time of publishing, we didn't run many iterations, but the trend is there, telling us that considering the cost information, the orange bar, we can actually do better. We can actually do better than the red bar. Cost information is helpful on a real-world data set, justifying our original intuition that we should plug in the cost for this application. Great, so cost-sensitive is better than traditional. Now, are people using our cool machine learning works for their applications like this one, for medical applications? If you see me ask this question, you may guess the answer. Okay, the short answer is no. Okay, people are not using those. Okay, so now let's wonder why. Why are people not using those for their applications? We have proved that we can do better. Okay, and the costs are inputted by the users. We solved their needs. They should be happily using our algorithm. Why are they not using it? Well, we have collaborators. So I ask our doctor collaborators why they are not using it. They're telling me, okay, that our model, our classifier looks good. Okay, they are really of low costs with the evaluation that we take. But they observe that this kind of classifiers comes with high error rate. So it makes lots of small errors. So the error is high, okay, but it avoids making super big errors. So in a sense, it's overfitting to the cost. Okay, it's overfitting to the cost such that it's avoiding the super big costs at the expense of more errors. So the error rate is just too high for them. Okay, they say the error rate is I don't remember the exact number, but maybe 30%, 40%, and that's not good. Okay, they cannot trust such a high error rate classifier, although its cost is low. So this is the cost-sensitive classifier that we produce. Okay, low cost, high error rate. I'm highlighting this in the red region in the cost error figure. So in this cost error figure, the vertical axis is the cost. The horizontal is the error. Each dot that you see in the figure is achievable by a classifier. Okay, so each dot is a classifier. You see that for some of the classifiers, that's low cost, high error. That's in the red zone. And for some classifier, low error, high cost, that's in the green zone. Okay, that was the classifier, the regular classification classifier that other algorithms produce. We produce the red one, others produce the green one. Neither are feasible for practical applications. What do applications want? They want blue ones, low error rate and low cost. Okay, that's what the application demands. So things are more challenging. It's not just the cost-sensitive classifier that we talked about throughout this lecture that we need to produce. We need to produce the blue one, low error rate, low cost. Now this is called cost and error sensitive, okay? And when discussing with domain experts, they suggest that it's more useful for their real world needs. Okay, did we succeed? Yes, we did. Okay, in 2012, we finished a work on cost and error sensitive classification that leads to this figure. And this figure tells us that for the cost, we can keep the cost to be low, okay, or even better, while improving the error significantly on every data set. Actually, the trick we use is simple. For considering cost and error concurrently, we just use a new cost function that's a linear combination between the original cost and the error. The linear combination between the original cost and the regular classification cost. Remember, we mentioned that regular classification cost is also a special kind of cost. So by this linear mixture, along with proper validation selection, we can get this kind of performance for practitioners. Good, so the story should be close to a happy ending. And I'm asking again this final question. Are people using those cool works for their applications? Well, the short answer is again, no. But this is for a very tricky reason. Okay, the students who took the lead in conducting this series of works with the doctors have graduated, okay, and chose to study in some other graduate schools in the US. So this project ended because we didn't find a proper successor for this student. Okay, so this project ended, and that's the best we did. Okay, we have an algorithm there, but we didn't have a good way to continue with the collaboration. And it actually shows that making impact for machine learning work is hard. We can identify new research problems along the way. Okay, we identify new research problems like working on real-world data sets, decreasing the error rate, and so on. Okay. But still, it sometimes requires very long-term relationship to get mature results. And anyway, after telling you this story on cost-sensitive multi-class classification research, I want to share with you some new thoughts that I didn't have maybe 10 years ago. First, things that we consider more realistic in academia may not be more realistic in applications. Many of us highlight that we want our research to be more realistic. And when we started research on cost-sensitive multi-class classification, we thought what we did was so realistic. Come on, we're putting things to the most general form. You'll give us any cost, I can solve it. Any cost, I can solve it. So general, so realistic, I can solve any real-world problem, much like a Swiss knife, right? Okay, you can use it in any occasion. But what's more realistic in application may be different, okay, because practitioners, application users may suffer from the problem like, okay, how do we do parameter selection, or in this case, cost selection, or maybe just simply inputting the cost is a burden for them. It's a 10 by 10 matrix for our doctors. What if we have 20 by 20? What if we have 100 by 100? Humans may not be able to input that, or people may have the question, should I put a 10 here, or 9.8, or 9.5? Okay, how does your algorithm correspond to or sensitive to exact numbers? Shall I give you the most sensitive number, or can I give you something looser, like relative difference? So real world needs, okay, starts from human, and considering what human means to be feasible is very important to be realistic in application. In academia, we do not always think that, and that's one gap, okay, that we all can think more about in the future. And another thing, cross-domain collaboration is important. Okay, with all the doctors, we couldn't have the chance to validate the algorithm on real-world data set. We couldn't have the chance to identify new research problems of being cost and error sensitive. Okay, and therefore, when you try to make your thing more realistic, consider cross-domain collaboration. And another thing, another important lesson that I learned is that it's not easy to win human trust because humans are somewhat multi-objective. When you do something well, they will find something that you didn't do that well and ask you to improve. Okay, so being able to keep improving your research within this multi-objective environment is important for winning human trust. But bear in mind, it's not that easy. Okay, so having said that, it's important, yet I consider it challenging to use Costsensitive multi-class or Costsensitive multi-label in practical applications. I welcome you to talk to me about other opportunities you may think of in the future, but it's not that easy in my thoughts. Okay, in summary, I gave you a lecture on cost-sensitive multi-class classification in the beginning, where we face two setups, class or example dependent. In the Bayesian perspective, which can be used in the class-dependent setup, I introduced you most importantly the Megacost algorithm from 1999. And from the non-Bayesian perspective, we can do data processing for expansion and then extend it to 1 versus 1, filter tree, other approaches to binary classification, or we can do one-sided regression or deep learning-based approaches. And if you're interested, there are some SVM-based implementations, okay, that you can check from my website, okay, to play with many of those algorithms. For cost-sensitive multi-label classification, we introduced you the PCC. That's a very representative family in the Bayesian case. And for non-Bayesian, we derived the condensed filter tree algorithm, which is actually strongly connected to the filter tree algorithm that we saw in the multi-class case. And there's another algorithm that I didn't have time to tell you that's a reduction to regression, actually. And most importantly, I wanted to share with you the application story that I had towards cost and error sensitive learning for bacterial classification. It's not totally a happy ending story, but hopefully the lessons that we learned along the way can be helpful for you to shape your future research. Okay, sorry about not considering the time, controlling the time that well. Actually, for the cost-sensitive multi-label part, finishing that algorithm would take probably 20 or 30 minutes more, so it may not be feasible, okay, for this setting. But I'd rather take this time to see if you have any last questions to ask me for our very last interaction here. Thank you so much for attending this lecture and this machine learning summer school in Taipei. I also want to thank our organizers for this wonderful event and hope that everybody gets the most knowledge back for your future research study. Thank you. And I'm switching to the chat panel to take any more questions. Okay, what if there is noise in the cost metrics used during training, leading to the discrepancy from one used for testing? Actually, this is a very good question. Okay? So to understand every research work, we need to understand the assumption, okay, that it takes. Most of the assumptions behind the techniques that I told you today assumes that when training, you are using the same cost metrics as in testing, except for one. The one work is the cost and error sensitive classification one. So in that work, we use cost plus error during training, but we use cost during testing. Okay, so that's one particular case that justifies it may be beneficial to use something different. But for using this something different, you do need to be aware that validation may be harder and things like that. And also, this question mentions about noise. And as you can imagine, there's a noise effect that may affect learning in cost-sensitive, as in any other classification data. But to the best of my knowledge, not many people have studied the effect of noise for cost-sensitive classification. So maybe this is something you can do if you can formulate it as an interesting problem scenario. How do you compute the final cost when comparing the cost-sensitive versus non-cost-sensitive approaches? Do you use the cost metrics obtained by the experts? Yes. Okay. The short answer is yes. The cost is always the same. Okay. In some sense, we fix the cost, we make it available to the algorithms if they choose to use it, and we use that cost to evaluate the algorithms fairly for their outputs. Okay. So in the application, more application scenario, like for bacteria classification, we use the same cost metrics. And for simulated data, like with the UCI data, we keep the cost metrics generated for both training and testing as well. If the training result is not good enough, how can we tune the cost metrics by observing the results? Okay, that's a good question. Currently, we only have limited experience on that. What we observe is that we may use the confusion metrics that you usually see in classification, okay, to digest what happened. So basically, if in some entries there's a suffer of huge confusion, this may hint that we need to adjust the cost in that entry to get better performance. So that's a rule of thumb, of course, and this particular rule of thumb is still in a very preliminary stage. So if you are interested in researching in this direction, that's certainly a possibility. Okay? But I can provide you my experience in terms of this rule of thumb. Why don't we use ensemble learning to take the results from multiple methods? Maybe we can put more weights on the CSMC predictions. Ensemble learning is certainly considered, okay, by many of the methods in the literature. For example, if you think about it in Megacost, ensemble learning is already used to get a better probability estimate, and they use that particular probability estimate to do the relabeling. Okay, and in methods like PCC, they also use ensemble learning to avoid the bad decision of choosing the chain structure, or in filter tree, ensemble learning can also be used to stabilize the performance. On the other hand, many people consider ensemble learning to be an added technique on top of the techniques that you observe here. So ensemble learning still needs to be coupled with some core techniques, okay, and to form a complete algorithm. And here the techniques that we discussed throughout this lecture can be helpful as well. Okay, so of course, okay, there's a potential that maybe you can use ensemble learning to, for example, decide better performing methods, and whether use selection or aggregation or whatever to tune for better performance. What was the team's priority between cost and accuracy? At that time, there was no priority, okay? But we try to formulate the problem in a way that we want to keep a similar level of cost while improving the error. Okay, so that's kind of putting things in a different side. Okay, for the cost side, we put it in a constraint. Okay, saying we want to keep the cost to a similar level while optimizing the error rate as much as possible. Okay, and I see many thanks here. Thank you so much for this feedback. I truly appreciate it. And I'm not in my best shape today. Okay, actually, I have to admit, okay, getting to the last part, I got a little bit exhausted. But luckily, with the feedback, the very interactive feedback from many of you, I'm able to tell you lots of interesting thoughts here. Okay, how do you see the scenario like episodic training for the future? I mean, the combination of feature extraction with classification. Yeah, that's certainly one possibility that hasn't been much considered. Okay, of course, for example, episodic training or more generally meta training scenario that people are considering hopes, okay, to initiate a classifier, okay, such that it can adapt to different related problems. Now, what if, for example, different costs are the different related problems, and whether that affects learning the right feature representation or initializing the classifier to the correct place? That's certainly something to think about. I haven't had much experience there, actually. I'm a novice in meta learning and episodic training, but I do believe there are interesting directions to be explored along the way. Human input is important, but their time is also limited. Would it be possible to learn the cost function for all classes by extrapolating limited inputs given by a human? Also, how to take evolving cost functions into account? Okay. And thank you for telling me that it's a great lecture. The short answer is, if you move to the scenario of adapting costs and maybe partially inputting the cost, I actually believe that reinforcement learning or banded learning like techniques, okay, like the one maybe you learned this morning, would be more helpful, where cost-sensitive classification can serve as good internal training components. Okay, but in terms of the protocol you're communicating with the machine, the protocol humans are communicating with the machine, like, okay, just partial cost or maybe time involving cost or whatever. Reinforcement learning is a more powerful setup, okay, that allows us to digest those. After digesting those, okay, you get a partial cost vector. Many of the techniques that we see today can actually be improved to take partial cost vectors as well, making the suitable choices for reinforcement learning. Okay, so that's how I see the connection between the techniques you learn today and the more realistic or sophisticated problem of getting human inputs. And I see lots more. Thank you so much for all the encouragements. And let's see, okay, do we have any more inputs from, actually our volunteers are posting your questions or thank yous from the chat channel that you use to the internal Zoom channel that I see. So there may be some delays and so on. So I'll wait for our volunteer to tell me that there are no more questions to end the lecture today. Okay, but before we end the lecture, thank you all again for being the attendance, and hopefully 15 years later, some of you can come back and become a lecturer, just as I do, okay? And you are very welcome to visit Taipei when the pandemic situation eases, okay, where you can get to observe, okay, this great place as well. Is it possible for machines to automatically learn the cost metrics to get the best performance? Thank you for giving such a good lecture. Okay, thank you for the feedback. And as mentioned, the short answer is yes. Okay, but it relies on several things. Okay. One is how can you give machine the information about the best performance? Okay, if you have a measure of the best performance, for example, best performance may be the best okay, for imbalance classification, or the best performance may be the best macro averaged F1, okay, for information retrieval. If you have a function to evaluate the best performance, then can the machine automatically tune the cost metrics to do that? You can put this, for example, in a reinforcement learning setting, right? Okay, you use the cost metrics as your state, and then the performance that you actually care about as your reward. Okay, and once you feed the reward to your algorithm with the particular costs that the machine explored as state. Okay, the machine should be able to optimize this if you give it enough episodes, okay, to lock in to the costs that gives you the best performance. But there are lots of if. For example, you will need to have enough computation power for this kind of reinforcement learning to work, right? And if you don't have that power, you want to do it efficiently, then it becomes a more challenging research problem that people in, for example, auto ML are trying to study. Okay, how to automate this process to tune for the best performance. Okay, so the short answer, you learn the core techniques. Can this core technique be coupled with reinforcement learning and so on to tune the cost metrics for best performance? Yes, okay, you can couple cost-sensitive learning with reinforcement learning with auto ML with techniques like this for optimizing your performance, much like how you can tune weights, okay, previously for better performance. But it's challenging. Okay, it's very, very hard, okay, because cost actually gives your algorithm lots of flexibility. And when there are more flexibility, things are much, much, much harder. Okay, I see more feedback on thank you. Thank you so much. Okay.
Yes, we have around several minutes to end the lectures. I think the student can grab their last chance to type the question, and when we are waiting for them typing the question, actually I have a general question. We have a general question for each speaker, so they can give some suggestion to the students. So my general question is like this. My general question to Hsuan-Tien is, your lecture influenced tens of millions of students, and you are also the chief data scientist in a industry, and you are also very experienced in the real world application. So when the student wants to use what they learn from the lecture to the real application, besides the cost sensitive issue you mentioned today, are there any other thing they have to pay attention? Thank you very much.
Okay, so let me repeat Hongyi's question. Hongyi's question basically says, in the real world, okay, in addition to those techniques presented, what are the important needs, okay, that people need to be aware of? I actually have one, I think, very important insight from years of working on real world applications. I think the issue that real world application suffers from is choice. Okay, so basically in every step of the real world application, we're trying to make choices. We're choosing between different models. We're choosing how to process our data. We're choosing how to tune our parameter. We are choosing, making lots of choices. For example, whether I should retrain my model each hour or each day or whatever. Okay, so in each level, we are making choices. And to succeed in real world applications, what we can do, what we need to do is to make each step of the choice as professional as possible. So it is not that we learn a super fancy technique and then we can succeed in the industry or in the application. No, we need to know many techniques. We need to know what are the necessary inputs in each level. We need to know the trade-off of each choice to convince people that we're making professional choices in each step. That's the only way to help us succeed in real-world applications. Okay, so for many of the students here, please do not imagine that you'll learn one of the sexiest technique or whatever and then rule the world. No, it won't happen. You would learn many techniques in your lectures, okay, during your study and so on. And in the real world battle, okay, the important thing is to make the right choice, or at least to pick the right weapon to solve your problem. Okay, pick the right weapon. It's important. You don't want to basically kill, in Chinese saying, okay, kill a chicken with a super big knife. Okay, for a chicken, you only need a small knife, and that does the job. You don't want to kill a chicken with a super big knife. Okay, and similarly, many of the techniques, not just machine learning techniques, but also data processing and any other techniques are very important. And another thing, okay, if I may add to that, is that don't just look at machine learning techniques. Real-world applications succeed by combining many techniques together. Machine learning techniques, traditional AI techniques, control techniques, statistics techniques, and maybe human embedding of domain knowledge or whatever. Combining those together, you can succeed. If you only insist on using machine learning techniques, most of the time you will find it challenging. So understanding different kinds of techniques, be open-minded in adopting them for your real-world needs, that's important. Okay, and I saw one question in the chat channel. Can we combine the cost metrics with self-supervised learning to get higher performance? And thank you so much for the good lecture. The short answer, I believe, is yes. Okay, but I haven't seen anyone done that before. Okay, so we'll see. Okay, the best I can say is I don't know, but I think it could be yes, or maybe okay, we can use, for example, self-generated costs as a kind of self-supervised scenario. Okay, instead of just self-generated labels, self-generated costs is another possibility that we can consider. But we'll see. Maybe some of you would come up with this cool research work in the future.
Yes. So thank you very much for Hsuan-Tien to be with us today. And thank you very much for all the very great answers, very insightful answers. So let's thank Hsuan-Tien again. Thank you very much for give us a great lecture. Thank you. So this
Thank you, Hong Yi, for the organizing team and the whole audience. Thank you.
Thank you. So this is the end of the second lecture of MLSS. So see you tomorrow.
See you. Bye-bye.
Bye-bye.